this lesson, we will first describe why it's urgent with a large-scale integration of renewables due to the risk for a serious climate change. Next, we'll explain that the transition to a close to 100% fossil-free energy system implies that the energy system has to be turned upside down, from a system where production follows demand to a system where demand follows production. This implies that the flexibility and intelligent operations to a large extent have to be moved from large conventional power and energy production units to flexibility and data intelligence at all types of end users. We will argue that some of the existing approaches for energy systems planning, power systems modeling, and markets have to be redesigned. Let us first take a look at the risk for climate change. Let's consider the CO2 content in the atmosphere as shown on this figure. When I was born in 1955, the CO2 concentration was around 310 parts per million. And when I became a full professor in the late 90s, it was around 360, while today it is around 410. It is expected that the climate reaches a tipping point when the atmospheric CO2 reaches around 460 parts per million. Let's take a look at the CO2 concentration for the last 10,000 years. You can see that the CO2 increase has been almost vertical since the start of the Industrial Revolution. Furthermore, it's well known that the CO2 stays in the atmosphere for thousands of years. Now, one could ask the question, if we stop emitting greenhouse gases, is that then the end of global warming? Unfortunately, the answer is no. If we have passed a planetary tipping point, then this is a point of no return, and the changes to temperature, probability of extreme winds, etc. will accelerate. Today, in 2090, roughly 50% of the Danish electricity consumption is covered by wind and solar power. Denmark has set rather ambitious targets. The goal is a 70% reduction in CO2 in 2030 compared to 1990. Today, we have reduced the CO2 emission with 32% since 1990, which implies that in order to reach the goal of a 70% reduction, we need to be 3 times faster for the coming 10 years. Is there any hope? The fact that the sun delivers the same amount of energy in 1 to 2 hours that the entire planet is consuming in an entire year seems to indicate that we just need to speed up. But it has to be now. In this and the following 2 lessons, we'll consider how we can help by transforming the energy system by digitalization and data intelligent operations. For our power system, the energy production and consumption have to be synchronized. Historically, this has been done by adjusting the power production such that the production follows the demand. In the future, however, when the production has to be based on fluctuating renewable energy, like wind and solar, then there basically exist 3 different solutions. Supergrids, batteries or storages, and flexibility. Flexibility can be unlocked by energy system integration and the use of artificial intelligence, AI. Traditionally, the focus for power system operators has been put on supergrids and batteries, but these solutions are very costly. It is my impression that for an efficient large-scale integration of wind and solar power, we need to look more into the possibilities by unlocking the flexibility by digitalization, AI, and energy systems integration. Consequently, the expected drivers for the green transition are more green and fluctuating energy production, increase the use of electricity everywhere, increase deployment of district heating and cooling net, sector coupling, including power to X, digitization and use of data intelligence, which means AI, grey box modeling, control, IoT, etc. Unlocking the flexibility at the consumer level. And finally, energy savings, which is still a low-hanging fruit in many cases. The basic tools for energy system planning and operations are still assuming that the flexibility is at the production side. However, since this is a wrong assumption for the future, where the flexibility has to be unlocked at the end users, this implies that many existing tools and methods have to be modified or redesigned. First of all, many tools for energy system modeling, like for instance Balmoral, the load curve is fixed to a level assumed at a given point in the future, like 2040. However, this assumption is not correct for the future. The assumption has to be relaxed since the end-user flexibility has to be taken into account in future planning and energy systems modeling tools. Today, electricity is bidded into markets using rather static bidding techniques, like a block bid with a duration and a volume. These bids are stacked at the given electricity market, and this leads to demand-supply curves. See the figure. These curves are used for clearing the bids and scheduling the production. This curve is static, linear, and deterministic. It will be argued in the next lectures that we need new digitalized and dynamic markets for the future. Given the market principles used today, the slope of the demand curve, the so-called elasticity, is describing the flexibility. And consequently, a simple number is then representing the flexibility in the conventional setting. However, if, for instance, a supermarket has been flexible for the past 15 minutes, then it might not be able to be flexible for the next 15 minutes. And consequently, we need a dynamic description of the flexibility, and we need to introduce the so-called flexibility function in the next lesson. In many countries, the main barrier for the green transition is, however, the regulatory framework. In the case of Denmark, the average cost of electricity is composed of 15% for the raw electricity, 20% for the net tariffs, and 65% for the energy taxes. First of all, it can be seen that we pay more for the transport of electricity, which means the tariffs, than we do for the energy. This indicates that either the electricity is way too cheap or the tariffs way too high. Furthermore, the tariffs and energy taxes, which is in total is 85% of the average cost, are constant. As a consequence of these structures for the tariffs and energy taxes, there are in general no incentives for being smart and for providing the needed demand response or flexibility for the green transition. The sad result of this is that the investment cost in infrastructure probably are way too high. These barriers for implementing smart and integrated energy systems have to be removed as soon as possible. As also stated by a new report for the Commission, drafted by Smart Energy Europe in Brussels. This figure illustrates a simulation with optimal dynamic energy taxes and tariffs, as outlined by the Danish Center for IT Intelligent Energy Systems, cities. We suggest the following structure for the energy taxes. Taxes should be linked to physics. The taxes should be linked to the actual CO2 emission, both locally, that means temporal and spatial. Taxes should be the same for all energy sources. Taxes should be the same for all type of consumptions. Taxes must contain a fixed part, which incentivizing efficiency, and a part proportional to the CO2 emission, which incentivizing flexibility. The total revenue can be maintained. It's simply a political decision. Most importantly, the energy tax should be linked to the actual CO2 concentration within the hour. Real-time CO2 values can be easily found for many countries. You can find more information in the provided references. Finally, we suggest the following main structure for the net tariffs. The tariffs should be instrumental in solving net-related issues. They must be linked to the physics. The tariffs should contain two components. One related to the energy, kilowatt hour, related to net losses, and one related to the capacity in kilowatt, and this should be both locally, temporal, and spatial. Stability issues are extremely important. Methodologies for implementing such tariffs for the green transition will be discussed in the next lesson.